So in part 9, we're going to look at some more advanced design topics. I decided to skip these in the earlier sections. They're not necessary in every network, but there are things that you need to consider, and we're going to talk about them now. So, actually, I should say security is always important, but we're going to look at other applications and things. And the first important design consideration is the number of users, or I should say number of devices, because a user may have several devices. And if you've got too many devices on your network, they will overload the AP. And the first way they can overload the access point is if you've got 100 or 200 devices and they're all trying to establish a connection with the AP, then its processor will get overloaded and crash, just like a computer. And the second way that it can crash is it's only got a certain back-end LAN connection. So you've got one data cable going back to your switch. So even if you've got a small number of devices connected to your access point, if they're all doing video conferencing or something, then they're not all going to get the traffic that they want, and the LAN connection will become congested. You have to remember that each LAN connection, each user, the AP is adding its management traffic, and the LAN is adding its management traffic on top of the actual data. So the amount of data connection that you think you have is actually less. And there are ways to avoid this. One of them is traffic shaping. You can throttle users, or you can throttle applications or ports. Some access points have dual connections, which are always appreciated in these situations. So 40 to 60 devices can overload an access point. If you've got a room, like in a classroom, an auditorium, a waiting room, an arena, then your access point has good signal strength in the room, but what it doesn't have is a capability of handling all the devices. So in that case, you have to add more access points to the room. So you might have a room that's 100 feet wide, and you need 5 or 6 access points to handle all the devices. And then, of course, you can use a much larger overlap. Just make sure to change a channel on each AP so that the overlapping access points have different channels. And also can consider if you've used a cloud managed access point or certain access point controllers, they can automatically configure the channels to avoid the interference. So what you need to consider again is the number of devices connecting, the type of AP you've installed, how powerful is it, its encryption protocol. Encryption makes an AP slower, so encryption means that access point can handle less users. Think about what kind of connection you have between the access point and the switch. How much data is being transferred by each device? So are people watching movies, or they're just checking their email? That's going to impact the number of users you can handle. What kind of devices they're using, cell phones, tablets, computers, and also the percentage of time a device is active on the network. So we find People in a conference room, they're all talking. They may not necessarily be doing things on their laptop. If you look at people are watching a football game in a stadium, they're not on their phones, they're watching the football. And then when the team takes a timeout, everybody gets on their phones and starts tweeting and watching video and whatever. Now Wi-Fi use goes from say 20% to 90%, and you need to be able to accommodate that. Manufacturers put out specs. Of course, their specs are based on controlled tests. They don't actually work in the real world. So, yeah. And then you need to consider wide area networks. So, if you have many offices and they're connected via WAN, and you've got Wi-Fi in every office, and now you've got a situation. And we're going to talk about how to handle that situation. The main problem is that you've got switches and access points in every single office, and then you might stick your AP controller and your servers only in the head office, and then all that AP traffic goes over the WAN, and all the traffic to the application server goes over the WAN. And remember our diagram from the previous part. So we've got our office, our typical office. We've got our access points. We've got our switch. Switch is connected to a controller. It's connected to a server. It's connected to a router. Router connects to the internet. This is our typical local office. If we take it one step further, with a WAN, our application servers can be in the head office, and we run the Wi-Fi over the WAN. The problem with that is that we have poor performance because all that traffic travels across the WAN, and the time that the traffic takes to get from an access point in a local office all the way to the server in the WAN, and over the WAN, and then to the server in the main office, that takes a while. Unless you have a very low latency WAN connection, which is very expensive. So if I show you how that looks, let's say now we've got our branch office here, and we've got our access points, our switch, our router, and the router is connected to the internet, which is this is our WAN here, and we've got our head office, and in our head office we've got our switch, and we probably have access points, we've got our controller, we've got our router, we've got our servers, and we're connecting our router to the internet. So now our AP traffic is traveling to the switch through the router. This is pretty fast. And then over the internet, the traffic is kind of slow. When it's hitting the main office, it's fast again here. So this is a problem. If this area is too slow, then the people in the branch office are going to be experiencing high latency, and they're going to be frustrated. So don't do that. Our second scenario is to put our servers and controllers in our head office and our branch offices. And we have a better performance here, but obviously it's more expensive. So you may decide it's too expensive. You may do it in some offices and not others, depending on the size. And what that looks like, again, is exactly like our previous scenario, but now we've added server and controller in our branch, and now the traffic goes from our AP to the switch to the server and controller here, and it handles it locally. And another advantage of this that we'll talk about later is redundancy. So if a server or a controller failed here in the branch office, then these access points would switch over to the WAN, and they would send their traffic to the main office and talk to a server or controller in the main office. And of course, you could probably think of this the other way around. If a server and controller failed in the main office, we could send our traffic from the main office to the branch and use their server and controller. Probably not though, because the branch is much smaller, so it probably has a much smaller server, much smaller controller, and they can't handle all the traffic from the main office. Anywho, the second thing you need to consider, as I said, with redundancy, add more data drops than you need. You know, running another cable, even another 300-foot cable is only going to cost you like $100 at the most. Maybe thousands if you had to come back and run a cable later on because your APs aren't dense enough and the users are complaining that they're not getting onto the Wi-Fi. So adding drops in the ceiling and just leaving them is a good idea. You know, it's future proofing. At some point your client is going to come up with another application that's going to work over Wi-Fi, or more devices are going to show up in the organization. I mean, it's going to happen. It's not rocket science. It's happened before, and you need to deploy more access points. Now you've got the cabling capability. So if you want to beat your competitors, you can tell your client this. You can't just, add more drops and add the cost to their bill. You have to explain to them the advantage of adding the additional drops now. And you have to also think about, depending on how complicated the construction project is, sometimes you can only run the cable during construction. Once the drywall's in, maybe you can't run any more data cable. So having them in now is clearly a smart idea. And then you need to consider, how do we design a system that functions completely even when an access point or a switch fails, which is totally possible, but you need to consider the return on investment, because additional equipment is more expensive and it has to be maintained. Not really, but you have to pay for it and install it and configure it. Do you want to spend the capital cost to make the system redundant? Now, to provide coverage in the event of an access point failure, it's very easy. You just add more access points. You increase the density of the access points until you have pretty much 100% overlap in the coverage area. What I mean by that is we make our coverage way, way, way more irritating. So now, if an access point dies, we've still got coverage. Not a big deal. Of course, if a whole bunch of them dies, which is extremely unlikely, we don't have coverage anymore, but that's not really a possibility. So we can have a failure of a single switch, which would result in a failure of the access points that it's connected to. Now, if we stagger our access points and connect half of them to one switch and half of them to the other switch, or to several switches, and one switch fails, then only the access points connected to that switch will fail. And if we've got coverage overlaps that are high enough, then the users won't really notice. And the way that we do that is, let's say we've got 5 access points here and they're all overlapping, and we've got two switches, and they're trunked together now. So, like I said, we're not using the full capacity of each of these switches. If you think about it, these are 24 port switches, and we've got, only 3 access points on one and 2 on the other. And the top one decides to fail, and now the link is down, and those 2 access points are down. So now we've still got 3 access points running, and we've still got coverage for most of the area. And if we improved our density even more, we would have pretty much no loss in coverage. And then we need to consider having a redundant controller. There are 2 options really, or 3 options I should say. The first option is installing 2 controllers on your LAN and having some APs assigned to the first controller and some assigned to the second controller. Now, if a controller fails, the access points assigned to the other controller to the failed controller can fail over to the one that's still running. The other option is assigning one controller as the main controller and one as a backup. And the reason is that this is a little bit better than having 2 controllers operating, is that when a controller fails, if the access points move over there, it takes a period of time for the access points to reestablish their connection with the second controller. And so if only half of them are establishing a connection, you've got half your network up. Whereas if all of them are establishing a new connection, then your whole network is down until they've connected. And the third option, obviously, is to put the controller on your LAN and then another controller in the head office somewhere. And I showed you earlier how that works. It's a very good option if you have a WAN. If you don't, then you don't. Of course, controllers are very expensive, so you need to consider how much ROI you're getting by making it redundant. Many companies don't use redundant controllers simply because they're too expensive and they don't have the budget. And we need to consider roaming, especially if you're using a voice over WLAN. As I've been saying, access points have coverage zones. So if you're on your voice over Wi-Fi phone and you're walking around in a campus or a big building, and you move from one coverage zone to another, and then you need to disconnect from the first access point and connect to the second access point. We call that roaming. And the connection between the device and the access point is disrupted, but the connection between the device and the internet technically is not disrupted, and that's because the Wi-Fi card has all kinds of firmware, and the internet itself has all kinds of software. It doesn't necessarily close a connection unless one party doesn't hear back from the other party for a long period of time. On a phone line, it's much worse though, so you need to have a roaming period that's less than 150 milliseconds, which is doable. And what I mean by that, this guy doesn't have a phone, but he's connected to our first access point here, and if he decides to take a walk, he ends up here, and now he disconnects from the first access point, and his laptop connects to the second access point. So he's okay, but we need to make sure that the overlap between the two access points is high enough that he doesn't experience a disruption in his connection. On a laptop, he's okay, but on a phone, he may experience a dropped call, and that will be very frustrating. And the other thing we need to consider when roaming is the IP address. So we're hoping that all of your access points are on the same subnet, but on a large network that's scattered everywhere, depending on how it was configured, the access points may be on different subnets. So if a device moves from a first access point to the second one and it's on a different subnet, then it doesn't get to keep its IP address. It has to get a new IP address on the new subnet. And that's totally irritating, but it's fixable. You can run a program called Proxy ARP or Mobile IP, and they solve that problem for you, and they do that by holding on to the old IP address and then getting your device a second IP address on the new subnet and forwarding the traffic. And another design consideration you need to think about is when you have several floors in a building, then you have signal bleed between the floors, and you can measure signal bleed during an active survey. And if it's a high signal bleed, then you need to stagger access points, because you don't necessarily need as many access points as you thought you did. I can show you. So if we've got our building and we've got 3 floors, and we stick our access point here, now we've got coverage through all 3 floors. So we don't want to add an access point right here, and then we end up with a circle because we are missing our coverage area here, missing our coverage area here. In reality, this is not going to be a perfect circle because there's still going to be some interference. And in fact, as I show you, it's going to probably be more like a wavy. It's not a big deal. You're not necessarily needing coverage right up in the ceiling or right down in the floor. So, and your AP is going to be horizontal. It's not going to be vertical, but you get the picture. So we can put our second and third AP here and here, and our fourth AP here, and we've pretty much covered the building. Keeping in mind the coverage is a sphere. I can't really show you 3 dimensions, but that's a general idea of how to install access points when you've got signal bleed. And then you need to consider a 2.4 or 5 gigahertz. So as you know, network devices, Wi-Fi devices operate on 2.4 gigahertz or 5. Newer devices can operate on 5 or 2.4 or both. So 5 obviously has a better performance and lower noise, but as a result of that, the 5 gigahertz signal doesn't travel as far. And the other thing you can think about is 5 gigahertz has 23 channels. So in a high density application where many APs overlap, you have many channel choices that you can use to make sure that the overlapping APs don't use the same channel. On a 2.4 gigahertz signal, you've got more noise, but your signal travels farther. And you need 2.4 if you're supporting all devices. So you should probably install access points that support both, unless you don't have any 2.4 gigahertz devices in your network, and you can turn off the 2.4 gigahertz frequency down the road once you phase those devices out. The other thing you need to consider is that since the 2.4 travels farther than the 5, you need to adjust the power on the 2.4, make it a little bit weaker, so that your 2.4 and your 5 gigahertz signals travel the same distance from the AP. And think about what country you're in, because FCC doesn't have a problem in this case, but other countries regulate which frequencies you can use. When we say 2.4 gigahertz, we're actually, we've got 11 channels. You know, it's 2400 megahertz, let's say channel 1, and 2420 megahertz is channel 2, and 2440 megahertz is channel 3, because a channel is 20 megahertz wide. So some of those channels are illegal, and you have to turn them off. So figure out, which channels you're allowed to use in your country, and if you've got a Cisco access point or some other access points, and you tell it the country that you're in, it'll automatically turn off the channels that you can't use. And then, as I said earlier, we can manually turn off the channels. We can also adjust the transmit power, to adjust the range that the signal is on. Data rate, channel width, fragmentation, those are all things you can adjust. You can adjust them granularly per access point. Of course, you can also set up Cisco radio resource management, and it automatically adjusts access point powers and channels. It does that by collecting data from the access points on your network and then adjusting the power and the channels. And if you install a new access point on an existing network, then RRM will take all the data that it has and automatically configure a new access point, monitor it, and adjust the neighboring access points so they all work together. Meraki's and other cloud managed access points do the same thing. They just do it over the cloud instead of locally. It's very useful, especially in a dense network where the access points are overlapping